Hello, everyone, and thank you for being here for another Big Astronomy live event. This event is Meet Gemini South, and we are honored to have Manuel Paredes here with us, who will be speaking about the Gemini South Observatory. Manuel is NOIRLab's outreach manager in Chile, so he's in charge of helping people all over Chile learn about some of these fantastic National Science Foundation funded telescopes. This event is part of our Big Astronomy program. Big Astronomy is the National Science Foundation funded program that includes a planetarium show created to help people understand about these fantastic telescopes in Chile, but also about the many diverse people and with different skills and backgrounds that it takes to make big science and big observatories happen. So the program includes a planetarium show, but it also includes these live events that directly connect you with people who work at these observatories, and it includes educational activities and educational research associated with the project. So if you'd like to learn more about that, I encourage you to visit bigastronomy.org, where we have all sorts of information there. We have more live events coming up, including one tomorrow about the Cerro Pachón Inter-American Observatory campus of about 16 telescopes just down the way from Gemini South in Chile. So stay tuned for more information about that as well. If you are joining us in the Zoom webinar, please make sure to select what language you would like to hear at the bottom of the Zoom window, because Manuel will be presenting in Spanish today. So if you will be listening in English interpretation, just select English, and if you'd like to hear Spanish, just select Spanish. If you are watching us on Facebook Live, you'll be hearing the Spanish presentation. So go ahead and join the webinar with the link that's included in the description so that you'll be able to hear the English interpretation. And with that, I'd like to turn it over to Manuel to tell us about Gemini South. Thank you for being here today, Manuel.
Hello everybody, and thank you very much for the invitation. I'm going to start sharing my screen. And there we go. So we're sharing the screen now. Oh, excuse me. There we go.
El comienzo fue un Big Bang y fue caliente.
Oh, perdón, no sé qué pasó.
I'm sorry, I'm not really sure what happened. I apologize. I'm having a bit of an issue with the sharing of the screen. So if you bear with me, please, for a moment.
Okay, there is. Creo que ahí está.
I think that should work now. Yeah, can everyone see me? Yeah, you guys can see the video? Well, everything actually started with a Big Bang. So some 13 billion years ago, and everything was very hot back then, right? So around So the universe has adopted this most marvelous, beautiful forms that we could ever imagine. So I'd like to welcome everyone. My name is Manuel Paredes, and I work as an outreach manager for NOIRLab here in Chile. And I'm going to talk to you about one of our research, astronomical research centers that has a particular trait of actually having two telescopes in two of the best places in the world to perform astronomy. And I refer to the Big Island of Hawaii and the north of Chile. Together, both Gemini telescopes can access the sky of both hemispheres. And another particular trait that it has, it's a consortium of 6-member countries, including United States, Canada, South Korea, Brazil, Argentina, and Chile. Now, all of this is a reflection of something very beautiful that has to do with astronomy, which we don't really see it in many areas of knowledge or any fields, because astronomy is a perfect field for collaboration, for international collaboration. And for example, at Gemini, we have about 100 people working here in Chile, and there's another 100 people that are also working in Hawaii. And of those people, most of them are Chilean and American as well. However, in this observatory, we have nationalities from Argentina, Brazil, Canadians as well, people from Korea, from Dutch people, Swedish people, French, Germans, Chinese, French, etc. And all of them are specialists in their particular areas and in fields that go from computer support information, administrative support as well, and all the way to physics and astronomy itself, but also seeing a series of specialists also in mechanical engineering and electronic engineering and electricity as well, in optics, and technicians from a variety of different specialties. And thanks to all of these people, it's been possible for Gemini to achieve several technological and scientific milestones, and we collaborate actively in following up on astronomical phenomena. For example, an interstellar visitor. It was a collaborative work that Gemini did to seek crucial observations to distinguish Oumuamua, a strange foreign object that visited our solar system. And after it was discovered in Hailakela, the both Gemini telescopes, both north and south, devoted themselves exclusively to observe it for 3 nights in a row before it would disappear very quickly from our eyes, from the eyes of our telescopes. So the researchers found that despite its stellar origin, it's very similar in its composition to some bodies found in our solar system, but its shape is different from anything that we had ever seen before. Another of the major collaborations that Gemini has done, specifically Gemini South, it has to do with the simultaneous observation of the first event of gravitational waves. When the Gemini South telescope used all of its available resources to observe a source of gravitational waves that for the first time, what we got to capture in infrared and optical light of the fusion of 2 neutron stars. It was the first time that humanity had ever witnessed an event of such magnitude. And thanks to observations performed in Gemini South, in the infrared spectrum and active spectrum, over 20 nights in a row, we managed to demonstrate that the mechanism of fusion for binary neutron stars causes a wave in space and time. And during the process, during this fusion process, these events form and disperse elements such as gold, for example, out into outer space, which resolves a decades-old mystery of the origin of the heavier elements in our periodic table.
LIGO observation was triggered, we didn't know what we were observing. Image of those galaxies. And the second night, we had more requests on the same target to be observed and those groups of people. So we realized, okay, this observation is very important. A lot of people want to.
Muchas personas quieren observarlo, así que tenemos que ejecutar el programa a la perfección, de lo contrario vamos a perder.
Hours at the beginning of this trigger happened. So every night we were losing time to observe this target and getting data. So the observer was very nervous, and also the operator was nervous not to make any mistake and check the instrument to work perfectly.
Bueno,
it was great because we feel that we were contributing to an important event for astronomy. And in fact, it was the first time that we image this kind of events in astronomy.
bueno, esos son dos relatos de personas que trabajaron directamente.
Those are two accounts from telescope controllers and astronomers who worked directly on this project, but I can also share some details. For example, when they were observing that, at the time, we were visited by the director of the observatory. She was the director at that moment. And it took her only 23 minutes to approve the observation proposals, considering that the approval process generally takes several months. I particularly had to go there one of those nights. I had to go to the office and see in the control room how people were working. And I thought it was very interesting because everything seemed a little bit secretive. But a couple of days later, we had a meeting with the director, and the director eventually told us what was happening and that we should get ready because they were going to release a press release all over the world along with other institutions, and we were going to announce this marvelous discovery. And it was actually the first time that we had ever observed gravitational waves, and it was the first time that we obtained live imagery of such an event. And as I said, it was for 29 consecutive nights we did those observations. Now, another of the more important milestones in Gemini is what we're showing right here. It's the system, the multi-conjugated system of adaptive optics of the Gemini Observatory. It's also known as GEMS. GEMS, S-J-A-O-G. It's a technological breakthrough that allowed us to observe the universe as a way we'd never had before. It was not possible to do this with telescopes here on land before. We know that space telescopes have a very good resolution, but we obtained the same resolution practically with this system. So this is how we saw how stars twinkle, but in fact, the stars are not flashing. Passes through the Earth, passes through the atmosphere, it distorts the light of the Earth, and it distorts it. And that gives us the impression that stars are twinkling. The Earth's atmosphere has several different layers with different temperatures, and when light passes through these layers, it doesn't go straight. It gets bent and it's distorted. When we see, for example, when you look over a heat source like fire or flame, we see the images seem to move. They're not well defined. And that's the same effect as when we, from Earth, look up at the stars. And that's why when we're looking at the stars at night, it seems like stars twinkle. And for this reason, Gemini scientists have worked for more than 10 years on designing a system which resolves the problem of atmospheric distortion in large telescopes. And the result of this work is the Gemini Multi-Conjugated Adaptive or Optics System, or GEMS, because of its English acronym. A technological approach that will allow astronomers to obtain images of a similar or even better resolution than the ones obtained from spatial telescopes, but with the advantage of being located on the ground. when we're using a telescope that's located on Earth, we're looking through the atmosphere. So there are images that you will see that will lose some quality because the Earth's atmosphere distorts them. But one solution is to make telescopes orbiting around Earth. For example, we have a telescope that's very famous, which is the Hubble telescope. Being above the Earth's atmosphere, the Hubble Space Telescope has no problem in capturing high-resolution images of the universe, unlike the telescopes located on Earth. This is its main advantage. However, spatial telescopes are very expensive, and there's size limitations when it comes to sending them to space. For example, the Hubble telescope has a diameter of 2.4 meters, but the telescope behind me, the Gemini, has a diameter of 8 meters. So with our telescopes on the ground, we have this problem of losing resolution because of the Earth's atmosphere. But at the same time, we can also build much larger telescopes, and we don't have any problem for performing maintenance. With adaptive optic systems, we can correct the effects of the Earth's atmosphere, and we will have an image quality just as good as the telescopes that are outside of the Earth's atmosphere. And we'll have all those advantages of having a telescope right here on Earth. So with this system, we can record images that are about 10 to 20 times larger, and will cover an area of observation 10 to 20 times larger than the usual adaptive optic instruments here on Earth. So the laser reached Cerro Pachón in March of 2010, and after being carefully assembled and then mounted inside the laser service enclosure, we began the alignment work as well as the optic associated to, and finally, January 22nd, we successfully launched the 50-watt sodium laser beam. And starting from then and during all 2011, technical work was done to make sure that all the work was ready so the scientists could start using it in 2012. So GEMS, it's a complex of instruments that's formed by 3 subsystems. A laser bat, a system to deliver the laser into the sky called the beam transfer optics, and an optical bank called Panoptis. The laser emitted from the top of the Gemini South telescope will interact with the sodium layer of the atmosphere to create 5 laser guide star constellations that are artificial, and that way we can measure the deformation of light when it goes through the atmosphere and then correct them in real time. The laser is located next to the telescope, so after that, we have to transport the light of the laser into a small telescope to propagate it in the sky. This smaller telescope is located behind the telescope's secondary mirror, the Gemini secondary mirror, and to bring the laser from the laser bench to this projection system in the sky, we have a set of many mirrors. We have a system, as I said, with many mirrors that we call the BTO. And the third subsystem is the subsystem called Canoptis. It's an optical bench that contains sensors to measure the deformations of the atmosphere, and it contains these deformable mirrors that can correct turbulence. And once the laser propagates and creates these 5 artificial points in the sky, once we have them there, we're going to analyze them with sensors that are located in the cannon, and these sensors will actually measure how the stars are deformed. And with that information, we can move, we can deform these deformable mirrors that in real time will correct all of the turbulence from the atmosphere and will produce these high quality imagery. So the images that you're seeing right now are test images, but GEMS is showing extraordinary results. Back in 2015, researchers from the University of Bologna and from the University of Concepcion here in Chile managed to observe with an unprecedented precision this Lilem 1 and show that it's one of the few places in our galaxy where there's stellar collisions. It's located 30,000 light years away, more or less. Here, there's an image from another cumulus. It was discovered by GEMS in 2016. If you see, we can differentiate or resolve the stars that are at the center of the cumulus, which is a huge scientific advancement that will help astronomers better understand the age, formation, and evolution of our galaxy. Another technological wonder that Gemini has contributed to world science is an instrument that we're seeing right now. It's an instrument that it's a hunter, if you will. It's a planet hunter, extrasolar planet hunter. The Gemini Planet Imager, we call it. It costs approximately $20 million, and GPI started operating in Gemini South here in Chile in 2014. And from then on, it's done the first catalog of young exoplanets from the size of Jupiter, located approximately 100,000 light years away. Now, the GPI has a particular trait that can directly detect the light of an extrasolar planet. And the objective of this is to determine its mass and its composition. Currently, there are more than 4,000 known extrasolar planets, but most of them have been discovered mainly using indirect techniques. The particular trait that the GPI has, the Gemini Planet Imager, is that it's one of a kind, and what makes it one of a kind is the chance or the possibility of blocking the shine of a star to verify any object or any celestial body that's orbiting it. And at the same time, it's an instrument that's capable of obtaining the spectrum of anything that might be in the field of vision in order to measure its size, temperature, its gravity, and even the composition of its atmosphere if it were a planet. Now, how is it possible to do this? With a very expensive instrument that contains an advanced unit of adaptive optics that's incorporated within, and it uses deformable silicone mirrors. This image is showing for the first time the video of an extrasolar planet in its orbit around a distant star. It was Beta Picturis b, a giant planet with a mass from 10 to 12 times the mass of Jupiter. That video was done through a series of images obtained over a year and a half, and it shows the path of the planet in its 22-year orbit around its mother star. In 2018, some observations done with the Gemini South telescope and other Chilean telescopes like Tololo and Las Campanas played a fundamental role in the composition of the light echoes coming from an eruption, a stellar eruption that happened almost 200 years ago. The data obtained with Gemini South showed that the material that was expulsed from this explosion is the fastest ever recorded in this type of phenomenon. Imagine reaching the moon in just 20 seconds. That's how fast all of this material traveled through space, and it's unstable and within this huge star. It was produced during this solar eruption more than 170 years ago. Now, why am I showing these eggs? Well, we're going to talk a little bit about eggs and planets, because after decades of observations and explorations, including a visit from Voyager, Uranus showed us a secret, the composition of its clouds. Now, one of the key components of this planet's clouds was finally verified. A team of astronomers found a couple of years ago hydrogen sulfide, a very disgusting gas that people avoid. Most of these top clouds in Jupiter and Saturn are composed of ammonia ice, but apparently that's not the case of Uranus. These differences in atmosphere composition shed light on questions about the formation and the history of planets. For example, if a human ever went through those clouds of Uranus, they would be in very disgusting conditions because the smell would be revolting, and the exposure to its atmosphere, 200 degrees Celsius, made most by methane and hydrogen, what would make our astronaut unfortunately die on the spot within that atmosphere. Now, I wanted to talk a little bit about the primary mirror, because the primary mirror is one of the most important contributions that Gemini has made to the world. And specifically, its coding is very unique for a primary mirror with an 8.1 meter diameter. Here we can see it in all of its glory. It's a pretty big mirror, and it's very reflective, as you can see. So this is the core or the heart of our telescope. So first we have nickel chromium, then silver, nickel chromium again, and finally silica. But the problem is that silver does not stick by itself to the glass. We need to apply a covering of nickel chromium so that the silver can stick to the glass of the mirror. But silver also oxidizes, so over that we place silica as a coating to protect it. But that's glass, so once again we have to put nickel chromium again and create a protective layer. So that's why we have 4 coats: silver, nickel chromium, and silica. And they form rings because the magnetron covers approximately 1 meter. So we have 3 rings to cover the whole radius of the mirror. And this covering occurs thanks to 3 devices. They're found inside the chamber, and they're called magnetrons. And their job is to deposit the material on the mirror, be it silver, nickel chromium, or silica. A cloud of ions is created inside the magnetron thanks to an electric discharge applied to the gas, such as argon for the silver or nitrogen for the nickel chromium and the silica. At the same time, the magnets in the magnetron form lines of a magnetic field in which the ions begin to form, finally impacting a plate that is found at the bottom of the magnetron. When the material impacts it, a molecule is released and it falls gravitationally and uniformly over the entire mirror. So the coating process begins with a new covering. Now, unlike other telescopes, the mirror of the Gemini telescopes, they have a multi-coated coating. As Tomislav was saying, our technician, one of them is silver. And why? Because after many studies, we saw that silver was ideal for our telescope when it operates in the infrared spectrum or the near infrared spectrum. The Gemini South telescope is optimized to work in this specific range of the electromagnetic spectrum of light. And because when we're doing science within this spectrum, within this range, the detectors or the cameras that they're incorporated into the telescope, the detectors of these instruments have to be at a very cold temperature. They have to be, some of them can reach up to 80 Kelvin, about 190 degrees below zero and Celsius degrees. Because the idea is to not emit any noise when they receive photons from a celestial body, because let's not forget that we're observing celestial bodies that are very far away from us, both in space and time, and they're very faint. So these instrument detectors are extremely sensitive. Therefore, any type of thermal radiation affects the final image. And that's why the entire telescope is designed to work at a very low temperature. And that's also why the telescope is located more than 2,700 feet up in the Chilean Andes. And that's why there's a whole cryogenic system within telescopes. And this way, we have to keep these detectors at a very low temperature, which allow us to have the best possible observation within this range of the electromagnetic spectrum, the infrared spectrum, or the near infrared spectrum. So within this context, silver ended up being an ideal material because it has an enormous reflectivity and a very low emission of heat. All of the elements they can reflect light, they can absorb it also, and they can emit it as well. But silver is the material that we saw that the technicians saw and the optical engineers found was ideal to work within the infrared range and the near infrared range because they have a great reflectivity and low emissions. The only problem with silver is that the oxidation is black, which forces us to constantly maintain these primary mirrors. And the video that we're seeing shows all of the process, or actually it's just part of the process of the coating, which takes approximately 15 to 20 days. And many people are involved in the process, people from different areas, to collaborate and make sure that the telescope can be up and running as soon as possible, because during this period, the telescope is inactive. Now, finally, this multi-coating technique or multi-layer technique allows us to have a marvelous mirror. Now, obviously, this would be impossible without all of the people who work at the observatory. Observatory includes approximately 100 people here in Chile and another 100 people in Hawaii. And what they do is all work together to provide observation services of optimum quality using cutting edge technology. But the most beautiful thing is that these people, it doesn't matter the color of their skin, it doesn't matter where they come from, the language they speak doesn't matter. It doesn't matter who they are. They're all wonderful people, and part of their spirit is to contribute, and they always want to contribute to the exploration of the universe and contribute with their tiny grain of sand, their small contributions to this fantastic task that is astronomy. And at the end of the day, it consists of really explaining what the universe that we live in is actually like. Is there life beyond us? Are we alone in the universe? And other types of questions. So I'd like to thank you very much for your attention, and I hope that you enjoyed my presentation about Gemini South.
Thank you so much, Manuel. That was very interesting. And we have some questions from our viewers. There's a question on the Facebook Live event. Just a simple question, wanting to know how you decided on the name Gemini for this observatory.
Okay, es una muy buena pregunta.
It's a very good question. Now, Gemini, it's called Gemini because we have two telescopes. They're twins. They're identical. The Gemini project was born with the objective of having two telescopes located in two of the best observation sites in the world, which is the Big Island of Hawaii and the north of Chile. Now, the idea was to observe the sky on both hemispheres, but in one single observatory. But for that, we need to use two different telescopes. So the name Gemini was born because they're twins. They're identical. They have the same dimensions. They have the same paint even. It's almost like the people are cloned that work on these both projects.
Fantastic. A follow-up question is that a clarifying question on how, when the light crosses the atmosphere, it's like the infrared. So how does that work? You mentioned that the Gemini telescope can view and filter the infrared light, and I think that somebody wants to understand exactly how that light travels and why the atmosphere might make it be in the infrared.
Ok, muy buena pregunta. Muchas gracias
It's
por las
also
preguntas.
a very good question. I'd like to thank you for such good questions, actually. The truth is, light, there's not a single light. We could say that light is white, let's say. And why? Because it contains all of the colors of the rainbow, what we know as the rainbow, at least. Now, we only see, or light is actually a lot more than the colors that we see in the rainbow. Light is, it's an electromagnetic spectrum. It's electromagnetic energy, I'm sorry. And it has different ranges. And within those ranges, we differentiate the optical range, what we see with our eyes. That's why we can see colors of the rainbow, for example. But beyond that, beyond our eyes, in Gemini, we can see more. And we have instrumentation that allows us to observe in the range, in the infrared or near infrared range, which is a range or a section of light that us as humans cannot see with our naked eyes. Now, what's the point of observing that range of light? The point of this is that, for example, we can see areas that are covered of gas and dust in the universe, but the portion, but we can actually look behind this curtain of, we can see the stars that are forming, stars being born. We can also see areas that are extremely cold in certain celestial bodies, like planets such as Jupiter, for example, the moons of Saturn, for example, like Titan. So that's part of the electromagnetic spectrum, allows us to detect light in that special range, and that way we can see things that would be impossible to see in the optical range of light.
And finally, Miriam also wants to know a little bit about you. Where did you study and what was your path to work here at Gemini Observatory?
That's a good question, but the truth is, I'm not actually an astronomer. My specialty, now actually, I've specialized over the years in astronomy, actually, and in science observatories. But how did I actually get to this point? I really liked astronomy when I was a kid, and I had my own telescope. I was really curious. I like to find out how to observe space, how to look at the moon. So I had a very small telescope, but it really allowed me to see. I would go to the library. I would check out books that explained how you could use telescopes better. So at the same time, I was very skilled when it came to writing in terms of humanities. So finally, I took that path, actually. It had more to do with my own skills, but I always kept an eye on astronomy, at least as a hobby. And when I got the chance, or when I actually saw an ad, a job ad in the paper many years ago, I didn't think twice, actually, and I decided to apply for the job because they were looking for a journalist like me who had a background in science. And I didn't think twice. I applied. I worked very hard in the interviews in order to finally to earn this position, and it's something that I love to do. I've been doing it for almost 13 years now, and I love it.
Thank you. I love hearing about how people's path to finding their job, and that's what big astronomy is all about. Is that it takes people with many different backgrounds to contribute to science. We need the people who have the skills in humanities to be able to explain all the discoveries that the Gemini Observatory enables, and all the people who work on the observatory. We just have a comment that these events are very cool. They've already helped me with some answers, and thank you very much. So we have some very happy viewers. Thank you for your time today, Manuel, and we appreciate this overview of Gemini South. And thank you, Sebastian, for your interpretation as well. For our viewers, I just want to know that we have research associated with this project. And so if you would like to contribute to the educational research on this project, you can fill out a survey that we will link in the comments. If you complete the survey, you'll be entered into a drawing for a $10 Amazon gift card. And on Facebook Live, we'll have a focus group link as well. And if you join the Zoom room focus group, you will receive a $5 Amazon gift card. So there are opportunities for you to contribute to the educational research that is being done on the project. We have other live events coming up, like Big Astronomy, like this event today. Tomorrow at the same time, so 3 p.m. Chile time, 2 p.m. Eastern Daylight Time, we have a similar event, Big Astronomy Live Meet CTIO, so the Tololo Observatory of 16 or more telescopes on Cerro Tololo, and Juan Segal will be speaking about those telescopes tomorrow. And then the next event in our Big Astronomy series is Real People Big Astronomy, featuring Dr. Luis Chavillera, and that will be on November 11th, also at 3 p.m. Chile time. We'll be posting about those on our Facebook. They'll also be in our mailing list. So if you would like to learn more, please go to bigastronomy.org and sign up for our newsletter or follow us on social media. And with that, just one more big thank you to Manuel. Thank you for your time today, and I know everyone enjoyed it, and so did I. Thank you, everyone. We'll see you again soon.